Welcome to Differential Equations. This is section 5.4. We have a mechanical system. We have some masses, and these masses are all connected by springs. Each spring has a particular spring constant, and so if you set up the equations of motion for these masses, we get a system that looks like the following. M1, M2, M3 are the masses we have. K1, K2, K3, K4 here are our spring constants. And when you write this as a matrix, we get our mass matrix. We get what's called the stiffness matrix based upon the spring constants. And then that sets us up for our matrix differential equation system. I'd like to solve this. Now, M, this diagonal matrix, is non-singular, and so we can find its inverse. And in this case, because they only have diagonal elements, getting the inverse is easy. All I have to do is replace each of the diagonal elements with its reciprocal. And so by doing that, we get this system now, our second order system. Our matrix A is simply M inverse times K. All right, and so we can find the eigenvalues and eigenvectors for A and solve our system. All right, so in question 1, let's see what we are given. We have two masses. We have three spring constants. They are giving me my masses M1, M2. They're all 1. K1 is 0, K2 is 16, K3 is 0. And so we can put all that information together, and I get my stiffness matrix K, which looks like the following. M is simply the identity matrix, and so it is its own inverse. And so matrix A for our system is M inverse times K. But M inverse is just the identity matrix, so that multiplied by K is still just K. So I can look for the eigenvalues. So I form A minus lambda I. I found the determinant of A minus lambda I, set it equal to 0. Multiply the downward diagonals minus the upward diagonals. All right, so we grind through that. So what happens is this 256 is canceled by this negative 256. And so I get a simple quadratic equation to solve. And so I set each piece equal to 0. And so I get my eigenvalues of 0 and minus 32. The omegas are the square roots of these numbers. And so square root of 0 is 0. Square root of 32, I can split that as 16 times 2. Square root of 16 is 4. All right, so I've got my omegas. And so let me look at using the different eigenvalues to get the eigenvectors. All right, well, if I have lambda 1 is 0, and I plug that into my A minus lambda I, my matrix looks like the following. If I take row 1 and simply add it to row 2, I get a whole row of zeros. And so this is for my eigenvector V1. So V12 from this row is a variable S. If I plug that in now and expand the top row, I've got a minus 16 V11 plus 16S is 0. And when I isolate V11, I get S. So my eigenvector for this eigenvalue is V11, V12, but both of these are S, and if you factor the S out, you get 1, 1 as the eigenvector for this eigenvalue. All right, if I plug in the other one, which is minus 32, I get 16, 16, 16, 16 in zeros. I can multiply the top row by minus 1 and add, and so I do get a whole row of zeros. Same trick, V22, because it's from the second one, is S, and then I can solve for V21 as minus S. All right, so V2 then looks like that, and I can write that as S times minus 1, 1, or the book likes to write it the other way as 1 minus 1, but either one is actually correct. So I now have my eigenvalues, I have my omegas, I've got my eigenvectors. So the general solution is going to be a sum where we plug in our omegas, the omega i's, the eigenvectors. If we have a 0 eigenvalue, which we do in this case, we get the special case that looks like the following. So, what does ours look like? Well, our solution is a1 plus a2t v1. That's because we had a 0 eigenvalue. My other omega, omega 2, was 4 square root 2. That's there. And that goes with the eigenvector v2. So plug those in, 1, 1, 1 minus 1. And so if you do that, you get x1 looks like the following. x2, the following. Now they're almost identical, especially the omega 1 parts, where we had an eigenvalue of 0. So what happens? The masses are going to move linearly. Why? Well, because these are linear functions. They're going to stay a fixed distance apart because these are exactly the same. If you look at this part, which came from omega 2, they are exactly the same. The only difference is it is opposite in sign. So, same coefficients, same omega 2, but they're going to be moving in opposite signs. And so when they ask you about omega 2, they have equal magnitudes, amplitudes, but they are moving in opposite directions because one is plus and one is minus. All right, if we look at problem 2, we have M1, M2, they are 5. My spring constants are 15, 10, and 15. All right, so plug in the information. We get our stiffness matrix, which looks like the following. My masses have 5, 0, 0, 5. So this is easy to find the inverse. It's the reciprocal of the diagonal elements. And you can verify that these work if you multiply the two together. You do get the identity matrix. And so I form matrix A, which is M inverse times K. All right, so I take M, multiply it by K, and I end up with my matrix A, which looks like the following. So I form the determinant of A minus lambda I because I'm looking for the eigenvalues and eigenvectors. right, so put all that stuff in, multiply. So let's see, minus 5 at 25. All right, so looking at that, I've got a 25 minus 4, so a 21. So there's my characteristic equation there, quadratic equation. And so the nice thing is it factors easily into lambda plus 7, lambda plus 3. So I get two eigenvalues of minus 7 and minus 3. Now in the solution, they tell you they want omega 1 less than omega 2. So I could have written this a different way. I'm just going to relabel that the smaller one is square root of 3 and the larger one is square root of 7. All right, so if I use the eigenvalue of minus 3, plug that in, I can simply add row 1 to row 2, and I get a row of zeros. We've done this trick before. V12 is S. Interpret that for row 1 here, and you get V11 is also S. And so for this eigenvalue, I get the eigenvector of 1, 1. If I use the eigenvalue of minus 7, I get 2, 2, 2, 2. So multiply row 1 by negative 1 and add, and so I do get a whole row of zeros. Same trick we've used previously, so my eigenvector is 1 minus 1. All right, so that means that my solution has my eigenvalue and omega 1 there of square root 3 times its eigenvector. All right. And this one multiplied by 1 minus 1. So if I look at this piece, it's got a 1 and a 1. So they're going to be oscillating in the same direction, not opposite, because they're both plus, same magnitudes. Whereas this one, same magnitudes, but I got a plus on one and a minus on the other. And so they're going to be oscillating in opposite directions, but with equal amplitudes.